Good evening, guys. We're going to look at similarity today, or in the previous video we looked at congruence. We're now going to look at the other side of that. Our essential question: how can you determine congruence and similarity? And then your I can statement: I can explain how two geometric figures are similar when you can dilate, rotate, or reflect or translate the first to obtain the second. Similar. Two figures are similar if the second can be obtained from the first by a sequence of transformations or dilations. So remember what we've talked about up to this point. If you translate, reflect, or rotate, you have a congruent figure. Your new image will be congruent to the pre-image. Congruence and similarity: if it's congruent, it can be similar. If it's similar, doesn't necessarily mean that it's congruent. So do remember that a translation, reflection, or rotation does give you a congruent and a similar figure. Dilations do not necessarily give you a congruent figure, because a dilation will make your figure either larger, an enlargement, or a reduction. That, in what we're going to look at today, dilations do give you similar figures though. For figures to be similar, these two specific things need to occur. Corresponding sides of similar figures need to be proportional. So if the corresponding sides are all proportional, the same proportion or the same ratio, then they are going to be similar. Corresponding angles of similar figures are congruent. So let's look at an example where we're going to determine whether two rectangles, and in this case we have rectangle ABCD and rectangle WXYZ. We're going to look and see if they are similar. Right off the bat, we notice that the corresponding angles are going to be congruent. Because it's a rectangle, all the angles are 90 degrees. So again, looking at those corresponding parts, A is going to correspond with W. And if you notice, they're both 90 degrees. B will correspond with X, C will correspond with Y, and then D will correspond with Z. So those are all congruent corresponding angles. What we are really going to focus on now are those corresponding sides. We're going to make a ratio with the corresponding side measurements. We're going to simplify those to see if we get the same ratio, to see if it's proportional all the way around. So again, remember in a rectangle, with ABCD here, we know that DC is 13 inches. Well, we also have to recall that those opposite sides are going to be the same. So that means AB is also 13 inches. And then, since BC is 6, AD is 6 inches as well. And then again, in our smaller rectangle, YX is going to be the same as ZW. So that's 3 inches. And then ZY is going to be opposite of WX, so that's going to be 6.5 inches. So really with a rectangle, we just need to test the length and the width, because the opposite lengths and widths are going to be the same measurement, so we'll get the same ratios. Let's look at side AB and make a ratio with a corresponding side from the other rectangle. So AB corresponds with WX, this side here. So I'm going to make a ratio with their measurements. AB is 13, WX is 6.5. Now that is definitely not simplified. We can use division. 13 divided by 6.5, and we get 2 to 1, or 2. Okay? Now we're going to test the other dimension and make sure we get the same ratio. So let's look at BC and its corresponding side, which is XY, which is 3 inches. So we're going to be comparing 6 to 3. This one's a little more obvious. 6 over 3, or 6 divided by 3, is a 2 to 1 or a 2. Since those ratios are equal, then these two figures are proportional. Their sides are proportional, which makes this similar. And that is because when we set up those ratios, we got the same ratio in the end, the same simplified ratio. Now, you would have to do it for every side of the figure, but in a case of rectangles, we'll just be making two more of the same ratios because we can compare DC to ZW, which is this side here. So again, we'd be doing 13 over 6.5, which is equal to 2. We would then be doing AD, which corresponds with WZ up here at 3. So again, we'd be doing another 6:3 ratio, which is 2. So all around, those corresponding sides have a ratio of 2:1. It's consistent in both rectangles, so that will make them similar. Okay, our last example is where we're going to look at two figures and talk about the transformation that has occurred. We've got triangle ABC and triangle NOP. They look like they're the same shape. It's obvious that they're not the same size. So we're going to look and see what happened and then test to see if they can be similar. A, B, C. A is at 0.5. B is at 4.1. C is at -5, 2. NOP, N is at 0, and that's 2.5. O is at 2, and that's a half, 0.5. P is at -2, 1. So to find out if these are proportional, we can make ratios with their ordered pairs. For instance, we have A and N. Those are corresponding angles. They're in the same location in the triangle. So we've got A at 0.5, and we have N at 2.5. Now we talked about scale factor here. If we were to write a ratio comparing the image to the pre-image, in this particular situation, you don't really know which is the original and which is the new image. So you can just make a ratio. I'm going to do A to N. So that means I can just kind of set it up that way. 5 to 2.5 is a 2:1 ratio, okay? Because if we take 5 and divide it by 2, we get 2.5. Let's take the B and the O. B is at 4.1. O is at 2.5. Okay, let's look at our x's. 4 over 2 equals 2 over 1. And 1 over a half equals 2 over 1. So again, this is a 2:1 ratio. Let's look at C and P. C is at -5. Sorry, that's a -4. My fault. I'm so sorry about that. So -4, 2, and P is at -2, 1. So, trying to fix that mistake there. -4 to -2 is a 2:1 ratio. And then, of course, 2:1 is a 2:1 ratio. So, this is also 2:1. Notice that our ratios are consistent for all three sides, all three sets of ordered pairs, so this is similar. We're going to do more examples in class where we're looking at dilations, comparing the scale factors, making sure that they're similar. Also just looking at figures that are drawn, comparing their side measurements.